We have a graph in this question, so we do our Oizerga analysis. The origin we see 0, 0. The y-axis is kinetic energy in normal units, joules. X-axis and time, normal units. So therefore, any questions about the kinetic energy of the time will be read off the graph. If we take the kinetic energy and divide it by the time, well, that's the rate of change in kinetic energy. And the area is kinetic energy times time. Now, if we look at the units of kinetic energy, it's mv squared, so that's kilogram, and that's meter squared per second squared. Since the velocity, and you multiply it by the time, then the seconds go away, and we're left with kilogram meter squared per second, which isn't anything that's useful to us. So we see the two graphs, they both have 0 kinetic energy, and then the kinetic energy increases for astronaut X and for Y. And we look at this value for Y, it's like 50, and the value for the other astronaut is 100. So we notice that the kinetic energy of Y is 1/2 that of X. All right, so we read the context. X floats next to Y. They're floating next to each other. Positive direction is shown. Force against Y. X applies a force against Y, and that generates that graph. So we have basically, in terms of momentum, an explosion. They're together, X pushes off, and astronaut Y goes in that direction, and astronaut X goes in that direction. So what is the change in momentum of the two astronaut system and the change in momentum of each astronaut? The change in momentum of the two astronaut system. So if the system is these two astronauts, initially the momentum is 0. So the momentum afterward must be 0. There's nothing else going on here. So the change in momentum of the system must be 0. So right off the bat, we're able to eliminate two choices, A and D. Now we know the change in momentum of each astronaut. So if we want to know the change in momentum of X, is going to be m delta Vx. And we know the mass is 50. And we need to know the change in momentum of we need to know the change in velocity. However, we are asked to determine what the changes in momentum of the two astronauts are. And what we know is, since the momentum is initially 0, it must stay 0. So if this has a negative momentum of, say, 100, then the astronaut must have a positive momentum of 100. So what we know is the magnitudes of these momentum must be equal to each other and the directions opposite. So if we look at choice 1, this says the change is 0, which means they don't move away from each other at all. They have no velocity afterward, which is false. And then if you look at choice C, you could see, X has a negative momentum and Y has a positive momentum equal and opposite to each other, such that they both add up to 0. So we don't actually have to do any calculations for this question. We just have to determine that the system of the two astronauts has 0 momentum before. It'll have 0 momentum after, we know. So the change is 0. And then we have to recognize that the momentum, since there was 0 momentum to begin with, they must be equal and opposite to each other. So choice C.